happens at x equals 2? Okay, there's a hole. What does that hole represent or indicate? There's no value at that particular point. Okay? At x equals 2, f of x has no value. F of 2 does not exist. Okay. That's the problem that we have there. And then x equals 4, same kind of problem as x equals 2. F of 4 does not exist. Okay. All right, so if these are all the places where it's not continuous, then by sort of process of elimination, one could say that it must be continuous everywhere else, right? Okay. And pretty much that is the case in this problem. This graph is continuous everywhere except at these 3 points here. Okay. All right, now let's see if we can come up with a better definition for continuous than, oh, well, it's just drawing the graph and not picking up the pencil. Okay. Actually, let me give you an instance where picking up your pencil definition doesn't work. We take a look at the graph y equals sine of 1 over x. We've seen this function a couple times before. And the graph of this function is very complicated to draw because right here around 0, it gets really oscillatory. It's oscillating a whole bunch. And then as we get away, you sort of get this standard behavior like this. Now, I drew this graph without picking up my pencil, so it's probably continuous, right? Well, it's not continuous as we get closer and closer to 0. And in fact, let me change this a little bit and actually define it to equal to 0 at 0. This function right here, I can draw it without picking up my pencil as I sort of indicated here. It's got a value at x equals 0, but it's not continuous at x equals 0. Okay. So this notion of not being able to pick up my pencil sort of fails with this particular graph. So, how can I get a reasonable definition for continuity? And the reasonable definition comes from all the stuff that we've done so far. We're going to put a lot of the things we've done together and use that to talk about continuity. All right. So there's two things we need to consider when talking about a continuous function. There's continuity. Draw it down. Call that point C. If this graph is going to be continuous in C, if we're going to say that this function, y equals f of x, if we're going to say it's continuous, what we want to do is we want to say that as we approach C from the right, and as we approach C from the left, that our graph sort of goes to the same place, right? And that's what sort of this pick up your pencil sort of definition says, is that it doesn't matter which way I sort of come in to the point C. If it's continuous there, my pencil should arrive at the exact same place regardless of which side I come in on. Okay? So there's what's called interior point continuity. And that says that the limit as x approaches C of f of x is equal to f of C. When we we talk about continuity, we're talking about whether a function is continuous on a collection or interval of values. Okay? This is what it means to be continuous inside that interval of values. Okay. All right. Well, we also want to be able to talk about continuity at this point and continuity at this point. So continuity at the endpoints. Endpoint continuity. We can't approach both of those endpoints from either direction. So what we do is we say, I'm going to say this function is continuous here if, as I get closer and closer from the right-hand side, the limit goes where I think it should go. Okay? So the limit as x approaches a from the right of f of x exists and is equal to f of a. Okay? Or if I'm talking about the right-hand endpoint, the limit as x approaches b from the left of f of x exists, and it equals the value of b. Okay. So these are two notions of what continuity should be. It goes back and it deals with these limits that we've been working with. As a formal test of continuity, which we'll get to in just a second, let's take a look at the following examples. Okay. Let's take a look at the graph of y equals f of x equals the square root of 4 minus x squared, 2 less than or equal to x, less than or equal to 2. And then let's also take a look at the function y equals the floor. The floor function. This is the function that sort of takes a value and rounds it down to the closest integer. Okay. Just rounds any value down to the integer directly below it. Okay. Integer function. Okay. All right. So let's take a look at the graphs of these functions. The graph of the first function. What is that first function to graph of? If you were to graph that as a picture, what would you get? Anyone know? Yes? Sure. If we plug in the two endpoints, if I plug negative 2 into this, what do I get out? Negative 2 in here, I get 0 out. Positive 2 in, I get 0 out. If I plug in 0, I get 2 out. Okay. So this graph, if I was to go ahead and fill in all the other points, it should look something like that. This is the upper half, or the upper portion of a circle of radius 2, center of the origin. So it's a semicircle. Okay. All right. In looking at this graph, where is this particular function continuous? Is it continuous everywhere? Is it continuous over all of these values here? Does it satisfy the notion that if I pick a point on here and I come in from the left and I come in from the right, they both end up at the exact same place? So this particular function is continuous on the interval -2 to 2. Notice it's continuous at the endpoints as well. As I get closer and closer to -2 from the right, I get closer and closer to 0, which is exactly what I get if I plug -2 in. Same thing over here on the right hand side. So this function is continuous on the circle. All right. What about the second one? What's the graph of this one look like? This one is a little more complicated, I guess, in a sense to draw. And again, what I can do is I can start by plotting some points. Let's see. At 0, I get 0 out. In fact, every value up to 1 gets sent to 0. I'm rounding down. Rounding down to the closest integer. So then at x equals 1, the closest integer to 1 is 1. And again, same behavior. All the way up to 2, it's equal to 1. Same thing here. As I continue on in an upward fashion, I get this sort of stair-step behavior. Also, same kind of thing happens in the negative direction. This graph looks something like this. Okay. Obviously continues on to both directions. Now, same question here. Where is this function continuous? Well, let's see. That question is probably a little harder to answer than sort of the not continuous question. Where is this function not continuous? It's not continuous everywhere I have this jumping behavior. Okay? So this function is not continuous at integer values. It has this sort of jumpy behavior, which is definitely a problem. It's sort of, it's not even continuous on the endpoints because it fails this definition right here on the endpoints. All right. So, I think, let's see. I have enough time to give you a final parting thought. This is what is in the book referred to as the test for continuity. And it's a very, very straightforward idea. It basically says that a function f of x is continuous on an interval C on the interval, in the interval. F of C exists. Okay. So our function has to have values at all of these points. It has to have a value. If I plug in that number, I should get something out. Okay. The second one says that the limit as x approaches C of f of x also exists. So that means that as I get closer and closer to my f of x value, it gets close to some fixed number. And the third one says that the limit as x approaches C of f of x has to equal f of C. These are the tests for continuity. If a function has these properties, the function has all of these properties on an interval, it's continuous, and for us that's good news because that means we can do extra stuff with it. Okay.
So what's C?
What's that? C is any value in the interval.
So is it like all real numbers, or?
It's any real number that's in the interval over which you're looking at. For example, like with our graph here of the semicircle,
Right.
C is any value between -2 and 2. Right? So just pick your favorite C. There's a C value right there. Does this particular C value give us a function value? Yeah. F of C is right there. That's F of C. Okay? In this particular case, as I get closer and closer to the value x equals C, what happens to my function value? They get very, very close to that number right there. Does that number equal the limit? Yes, it does. But in this case, that semicircle is continuous everywhere between negative. All right, that's all for today. Thanks for coming. We'll see you back here tomorrow.